All right. The class is being recorded as we speak, and I'll go ahead and put that on same process of YouTube and a link to you guys. Okay, so the first thing we were trying to do is talk about the deliverables for the lab reports. And then the lab reports usually at the very end, it tells you specifically what you need to include. You need to include the stimuli. You got to say what the memory locations that are you're looking at, and you also want to talk about your test plan. Okay, those are typically, and then pseudo code is basically a high-level C-like way of describing what are the big tasks you're going to do in your program. And disassembly code, the reason I like this is because this kind of shows me and you that you've been able to compile the code correctly. You haven't had any error, and you've generated the machine code and shows you the machine code, shows you the assembly code and all that at the same time. And once you have this, you do not need to put your original assembly code in. So I think I have my MPLAB up, and I think this test was the previous lab that the LAB3 that we worked on together in the class. The source code is, that's not it. Let me open the source code. And this is the source code we wrote together in the class. And if I don't remember if we compiled it or we didn't compile it, so let's go ahead and go through together and compile it, which I usually click on here, but you can go through the menus and do it as well. This basically cleans out all the settings and everything and says, let's build it really clean. And then we watch down here, and you want to watch for any blue or red link, because if you have a blue or a red link, it means you got a warning and an error. And as we discussed before, this program is a little bit polite, too polite as far as I'm concerned, and it gives you a warning where it should be really giving you an error, and doesn't even, and it's kind of a little bit silent in that it doesn't tell you that it didn't compile it. It just gives you the error and it stops. So you want to make sure you don't have any in this output, any blue or red link indicating warnings or errors, and indeed at the end you get a build successful here. Okay, if you do that, that means you did an assembly code. The code has been assembled into a machine code, is ready for you to run it and debug it. Now the question that was raised by Daniel was that what is this assembly code? So if you go to debugging under Windows, you go to the debugging, you go to the output, and you click on the disassembly listing file, it shows it to you. Now you notice the first time you do this is going to be the thing you're going to get. It says, hey, I cannot generate this listing. You haven't told me I need to generate the debugging information and disassembly code. So all you have to do is go to the testing, right click on the name test, go to the properties, and there is a loading feature here. Just make sure you I think the only thing you have to click is this one, but what the heck, I'll click this one too to get the hex values as well. But I think all you need is load the symbol. But what it means is that I'm going to generate a full disassembly code for you so you can see where the variables end up, where your code ends up, and all of those kinds of stuff. So we go ahead and apply that, and it's all good and okay. And then we have to come back and reassemble again because it's got to go through the process to generate all the numbers. And when it's finished, this is a disassembly code. Now let's walk through this. This was your assembly code, right? This is the assembly code you wrote. This is the disassembly code. Now let's see what it is. Look, for all the comments you wrote, all the name definitions, port A's, FA, there is no assembly code. You see that? They are not assembly code. Those are just definitions for the assembler to do his job. The very first place where you have an assembly code is right here, clear F port A. And if you come over here, it says, oh, and then this is your assembly code, but everything is defined. All the optional things you didn't put in there is defined. For example, clear port A, you can also have a flag, which says if you're bank switching or not. And in this case says, yep, A is equal to 1. And they like to use constant names instead of using 1 and 0 because they think it's easier to remember. So access is 1, for example. And then clear F, and then see this code here? If we were to take clear F and write the machine code for clear F, we're going to get 6880. And then this is the address, which basically says where this machine code is going to sit in the memory. So if you go manually into the memory, let's say we got a problem, your memory is not working, you're a computer engineer, you're designing this hardware, your phone or whatever it is you're designing, yourself, driverless car or whatever, and your code is not ending up in the right place, you can actually look at your assembly, see where it's supposed to be, and then you go to look to see where it is, and then hopefully in that cycle you figure out what went wrong. So this is a disassembly code. This is the only code you have to include in your lab report. No, you don't need to include the raw assembly code. You need to do this. Did that answer your question, Daniel?
Yes.
Perfect. So now let's go to Tim's question. Tim's question was, okay, I've got this code, but it's really not doing what I want to do. How do I go about debugging it? Is that the right way to say it, Tim?
Well, so like, I thought I knew like how to run the debugger and do the thing. And like, I was firing different pins or whatever to kind of like add, different numbers, but everything was just coming out 0. Like when I was running through it, and like, it would get stuck in that loop, like the bottom loop, the waiting for the next thing, even when I would fire pins. So it was just kind of like, not entirely sure if I was doing everything like right, because I didn't get any answers except for 0, even if I was like firing pins or doing anything. And then it wouldn't jump out of that loop. And then like sometimes it wouldn't even like start from the beginning. It would just start in that loop. So there's a lot of different things kind of going on with that lab.
Let me do this.
Actually,
so since I don't have your code in front of me, let's do this. I'll go through the general way of doing it, okay, for this particular code. There are some gotchas in the simulation we need to talk about.
Right.
And if you have a very specific question, so Angelo has a really kind of good where you're firing the right pin. So we're going to go through all of that and talk about it in a minute. Can
I ask a quick question expanding on his question?
Sure.
So the loop, I pretty much use the same loop that you had where it would just branch back to the start unless it saw something different. I noticed if I didn't fire a pin before I started the simulation, then it would get stuck in the loop and it would never come out no matter how much I fired. So it's not actually testing at that point. It's unfortunately, I think that loop would be something that you're going to get stuck in unless it sees stimulus beforehand.
Well, we're going to walk through this. So let's walk through it and then engage. Let's bring up all these things as we go through it. Okay. So the first thing you do, you've assembled this thing, life is good. Then you should go to the debugging and you say, okay, debug my main code. So okay, I'm going to debug my main code. Although I really should have, what I should have done is come to the stimuli here, and I didn't. Well, and notice where I set it to high. This is not a good. This is a fine way to do it, but once you set it to high, firing it again doesn't do anything, right? That might be one of the problems. Does that make sense? So if it's high and you set it to high, does anything change? No, nothing changes. The way I do it, like to do it, I said I'm kind of lazy. So I set it to toggle. So when I fire it once, it goes to 1. If I fire it again, it goes to 0. If I fire it again, it goes to 1. So it's toggling back and forth. So it's always changing. So that might have been the problem you had, Tyler. Okay.
Yeah, I think that might be because I did change it to toggle eventually, and it did work. But
because once you set it to high and you fire it, then that's it. You know,
I assumed that it was high, and then when you fired it, it went to 0.
No.
I didn't realize it stayed.
If you set it to toggle, it would do that. Yeah, good point. Yeah, great.
Okay.
So let's just set this one. I mean, I'm not going to spend the class time going through and setting R0 through R7, but you really should have when you share this window. Oh, by the way, you can resize the window if you want, right? When you share the stimuli window with me, I'm expecting for you to have R0 through R7 set, okay? Because I want you to tell me that you know that the inputs are coming from RB0 through RB7. Does that make sense, everybody?
Yeah, that makes sense.
Okay. So let me do, see, this is operand 1, and I'm not going to worry about, so maybe in here, I would also add RB, let's say RB4, and let's go ahead and add one more, and RB5. So that's operand 2, right? Everybody with me on this one? Anybody has question what I'm doing here? We have 2 inputs coming in. One input was from R0, 1, 2, 3, right? Those were the 4 bits. And then RB4, 5, 6, and 7 were operand 2, right?
So port A should hold the value of 4 once we finish it.
Yep. So, so you put all of them, and I'm going to make these toggle for now so something changes, okay? And I'm not going to worry too much about what the values are right now. So that's one. And then on the output, on the variable side, I at least want to see port B, and I at least want to see port A, right? Because port A is where my output is coming out, so I should be able to see where that is. Always a pretty good idea to CW register also, okay? That's useful. So what I'll do is go ahead and add, and I don't remember, here is add, and I think port B, can I put port B in here? It's an SFR register. Oh, this silly thing.
I believe you already have port B. I think you need port A.
Port A, okay. Port A, Trish A and Trish B would be kind of nice to look at it to make sure you're setting it correctly, but it's not as critical. You can also look at the variables like operand. We put, let me go to the assembly, it's easier to look at. So for example, it would be kind of nice to see what, I thought I fixed that. I think Daniel pointed that out and I fixed it, okay. So some of the other one would be good. So I would also like to see location 83, at least the last value, because we use that to remember what it was before we jump. So maybe add that one too. So add 0x, oh, I might as well put everything in there. Okay, so I put all of that stuff in there. I wonder if I can organize them. Probably not. Anyway, so I put all that stuff in there. And then what I like to do is says, you know, this stuff is, I copied it from the previous one. There's nothing really exciting happening here. These are all the initialization. I'm doing it all the time. Nothing interesting. Really, the interesting things happen right here. Oh, by the way, if you try to put a breaking, let me stop. Let me pause this for a minute. So if I have a breakpoint here, you see that? So I'm going to stop this breakpoint, and I'm going to say, I'd like to know when, oh, actually, that's a fine place. So we'll get here. So, so you see how it won't let me put a breakpoint here? Because there's no code on this. This is just a reminder of where I want to jump to, right? The only place there is a code, a memory location, is where there is this. So I can put it, this is not valid, but this is valid. That's breaking point. What is a breaking point? Breaking point is when I go to the debug and I say continue, it will run in and stop right there. So this way I don't have to sit there and hit next step, next step, next step. Does that make sense? Any questions?
Okay, so like line 55, that's just like a specific address location.
Yes,
and that
yes,
white
because-
portion is just like pretty much saying it's the state, where it's like, say Washington, for example, but 55 would be like a specific location in the states.
Yep, you got it. So if I go here, I'll show you in here. This is the disassembly code. If you look, let's go to line 55. Where is 50? Oh, it moved. Okay. Start. Wait. We're right here. See, wait has no code or memory location associated with it. You see that? But the next line, so it won't let you put a breakpoint here, says, I don't know where in the memory that is, so I don't know how to stop there. But the next line, which has a assembly code, it says, oh, I know what you mean. You mean you want me to stop when it hits location, memory location 26. Oh, I got it. I can do that. Does that make sense, everyone? Okay. So now we're gonna actually let's go back here and let's go ahead and put the break. let's start at the beginning of this and walk through it together. So I'll put a breakpoint at the beginning of the code, and then we say, okay, I want to debug it, so I'm going to start debug all over again. So the debugger is going to run, and at some point it's going to stop. Once it hits that line, it stops. Now I have an option. I can use F7 to step through everything. So let's walk through it while we're watching the variables. So here I expect port A to go to 0. So port A right now, oh, it's already 0. So then nothing exciting will happen. So I'm hitting F7. Every time I see F7, you see the green that indicate which is the next instruction to be executed is moving. You see that? And you notice when W register got changed from its current value to a new value, it turned red. You see that? So next instruction is I'm going to put FF in Trish B, and I don't think it's going to change, maybe change color, but it's the same value that is in it, so might not change color. Oh, it did. Okay. Oh, W register changed color because we put FF first. It's got to go to W register before it goes there, and then W register changes again. But since Trish A, oh, I don't even have Trish A in here, so it doesn't matter. Okay, now we are here. So now I'm about to execute port B. So let me go and mess with the three. So I'm going to fire RB0 and I'm going to fire RB5. So hopefully, sometimes it doesn't catch it, so you got to do it a couple of times. But what I'm expecting that to have happen is that when I fire those two things, then the variable in port B should reflect that. So let's see if we got it. If it didn't get it, we'll go back and do it again. But oh, there it is. You see that?
I feel like if it's set on toggle, if you were to fire it multiple times, eventually one of the ports would be a 0 instead of a 1.
Yeah. Yeah.
Okay.
It's every time you hit it, it's going to change from what it is to its opposite. So if it's a 1, you hit it, it's going to go to 0. If it's a 0, you hit it, it's going to go to a 1.
Oh, okay. So like, say if I even, if it's a 0 and I fire the pin and the action is set to toggle, it'll go from 0 to 1 and never reverse back and forth.
Yes, it does.
Like,
if you toggle again, if you hit the toggle again, it goes to 0.
Okay, gotcha. So
That's the word. That's the word toggle means. Toggle means to go back and forth.
Okay, makes sense.
So when pins are set high, but you haven't fired them yet, do they start at 0? Like
typically, you're not guaranteed. You're not guaranteed, but typically they start at 0.
But when you fire them, they go to 1, and then they stay that way because that's And if you fire it again, it stays 1 because it's set high. And okay, I get it.
And I think that might have been your issue, Tim, as you went through it.
I think you're right. Yeah.
Okay. So now,
By any
let's
chance,
I'm sorry.
is there a way to see what it starts at, like in your stimulus window?
Yeah. You can look at port B, right? You look at value in port B. You see here, port B.
Oh, I guess if you just run it through, it'll tell you exactly where it is.
Yeah.
Okay.
Typically starts at 0. Typically, unless you ran the program before and you didn't clear everything up and all that. I think there's a way to reset everything, and I don't remember. Oh, here, you can reset everything if you want to start clean.
Okay, cool.
Okay. So we're going to single step it. Let's walk through it. We won't take too much on this one, just a little bit more, because this is a useful skill to have as programs get more complicated. You have to debug because a small error can kind of make you spin your wheel for a long time. So we're going to F7 it. So it's going to basically what he says is move F to W register. So I'm going to look for W register to become F. I don't want to highlight it because it looks like you can't read it. So W register, after this instruction is executed, watch the green. Green is telling you where you are, right? That's from execution. So I'm going to say F7, which goes to the next line. And sure enough, see W register went to F, value is F. You see that? And by the way, remember, I think it was Gabe or Vlad who told us about this little upper corner where you can get different things displayed. And that's pretty useful. I really like this. Okay, so F7, now it's going to put it in op1. And if I remember op1, that was location 80, remember? So location 80 should go to a 1, next step. And if it doesn't, then we got a problem, okay? Oh, I hit the wrong button, my apologies. I hit F5, which executed until the next instruction, next breaking point. So we had a 1 and a 2 in here. So now if I look at port A, how come I didn't put the, oh, we didn't put the values in. So I noticed that port A was supposed to have the output value, but it doesn't have the output value. Why? Now I can go back here and look at it and say, okay, I did the add, but I never put it in port A. You see that? So I came here, I created this, I cleaned it all. I cleaned port B, but I never added up A and up B together. I think maybe I didn't save this thing last time when we finished. So you came here and you say, what is the, so W register, okay. So I'm gonna move move F, I'm gonna move up 1 to W register. And then I'm gonna do an add WF, remember, so right, I'm adding W to F register. I'm gonna add up 2 to it, and I'm gonna put it back in 0. Put it back in W register. And then I'm gonna move WF, move what is in W into port A, which is where the sum should end up. Fair enough. Any questions so far? Okay. So now I have to restart everything. And what I'm going to do is I'm going to say, this is boring. We already know what's going to happen here. I didn't change anything. So I'm not going to sit there and single step through this. The exciting things really happen over here. So I'm going to put a breaking point here and watch it go through. Fair enough. And then we're going to that'll be done. Okay, so what we're gonna do is we're gonna rebuild it, debug it, and there we are. And then we look at our variables, and we see that, okay, so now we're gonna go to stimuli and say, okay, I wanna add a 1 plus 3. So I'm going to hit this one once. I'm going to hit the 3, this one, and this one. Since they were 0, they're going to hopefully turn into 1 and 1. We'll find out. And by the way, the stimuli is not going to be seen until you run the next instruction. So I'll come in and say F7. So now port B, I should be able to see what's in port B. Okay, it didn't see anything, so that's fine. Now I'm going to sit in the wait list because nothing is changing. So I'm going to go to the stimuli and let's hit one of these. Let's see if it sees it. Variable, F7, F7. Huh, interesting. How come it's not seeing my stimuli? I'm firing it. Variable. And I don't like
this.
it.
This is the problem that I was having. Because I changed the toggle and it was doing this for sure. I had to stop it and restart the simulation a couple times. And
Yeah, it could be that something went wrong. So maybe it's a good idea to just do a reset or shut it down and start it over. So let's try this again.
Yeah, I had the same issue, Tyler, to be honest.
Yeah, so maybe we should stop the debugger, explicitly stop the debugger and restart it. Let's see if that fixes the problem. So that might have been it. You have to explicitly stop your debugger and restart it again. Maybe we'll find out. So I'll go over here and I fire this thing, and we are here. Output variable. So let's do F7. No, F7. Okay, that's it. You want to explicitly stop, because if you don't stop your debuggers, it look like it does silly things to it. So that was great to see it. Yeah. Vlad, did you have a question?
Yeah, it's mostly about the wait portion.
Yeah.
Honestly, in my opinion, I think it's very unnecessary. To be honest, because essentially, usually if we allocate those pointers like start and wait, we would want to branch back to them. We could have a call to them or a ret fee or a return. But in this case, we're not doing anything with the wait portion. We're just allocating an address area, what is going underneath it.
You have a good point. You have a good point in that. I think if I understand you correctly, you're saying, look, during the wait, you're not doing anything useful.
Yeah.
Why not just keep adding it? One thing I haven't told you guys yet is that if you keep writing to the output constantly, every time you write, the output gets disabled for a short amount of time. So if you're writing the same value over and over into the real hardware, it's going to blink a little bit. So you do not want to keep writing the same value to the output if you don't have to. But your point is well taken. Based on the information provided to you, I think you're within your, it's a good argument to say, hey, I don't need to do this unnecessary wait business.
Yeah, I mean, essentially, it's just a comment in a sense saying what is going underneath that allocated state, what is happening underneath it. I'm mostly because I'm putting this argument is because I got a point doc for this.
That's okay. You can come and talk to me about your point later on. But
okay, all right.
But just this is a good practice. If you're not doing something new, don't do it. Basically, that's the idea here. So anyway, so let's walk through this. So basically, the loop, this loop will continue to run. Where am I? It's gonna do this, and it's gonna add the numbers, put it in port A, and then it's gonna just basically sit here, and it's not gonna do anything. It's just gonna sit in this loop forever and ever until you go give it something new to deal with. So if I give it something new to deal with, and hopefully that is a change. Yeah. So as you see, port B changed. So now when it comes to see, is it anything changed? The answer is yes, things changed. And so you're going to jump to start, and then you're going to start executing. Okay. So let me stop right here. Are there any questions that you have?
Yeah, my question is how, when you fire different stimuli in the middle of that particular run of the debugger, did it bump back to start? But when you tried to do that before, it didn't. Was that just like
So the reason it didn't do it, because the first time through, watch what happens. You come here, you get operand A, you get operand B. Okay. So if you made the changes before the sum was created, then that sum is based on the new input, right?
right?
So it does the sum, puts it in port A, and then when you get down here, then it takes the port B. So at this point, port B is what you have already changed, and puts it in last. So it's waiting. When it goes to here, it's waiting for your port B to change. Wait. So it's waiting for an input in this location. So if you change your input before this location, it says I already took care of it. There's no reason for me to do any more sums.
I'm just curious because I remember, like, literally just 5 minutes ago, we had to restart the whole thing to get it to like do that because you were trying to hit the thingies and stuff like that. Right. So is that a glitch in the MPLAB thing? Like
it isn't. It isn't. The issue was that we changed the code, but we never restarted the debugger. So the question, which code was it running? Which code the debugger was running, old or new, and what state it was in. By explicitly going up here and saying, let's stop the debugger, and then let's start it next time for the next piece of code that I have. Then you make sure everything is starting from a clean, known starting point.
Gotcha. Okay. All right. That makes more sense.
And that might have been a problem that Tyler and you may have encountered as well, where you maybe went to change your code, but didn't explicitly stop the debugger and start it over again. So
Yeah, that's probably true.
These are software codes that are not perfect. So expect some of those things that we can talk through it. And every version, they get a new thing going. So that's just the way. They fix some stuff, but some stuff breaks. Okay, let me stop here. Hopefully that gives you a pretty good perspective on how this whole thing works. Okay, so LAB3, you're going to need more of this to do. So the next topic I wanted to do is just see if you guys are okay with the stuff you're working on, and if you have any specific questions that is coming up that maybe we need to cover. So let me go ahead and find where okay, there we are. So one of the things I wanted to take a few minutes and go through is, each command, each of the commands we deal with has has a description for it. So it doesn't matter what the assembly code is that you're dealing with, they're going to have a full description written in here, and they follow some syntax you may not have seen. For example, if you ever see this epsilon looking character on the description of the thing, it's a set of. So for example, when here says a little epsilon looking thing, parenthesis, square bracket open 0, 1, square bracket close, it's saying a can be either 0 or 1. That's all it's saying, nothing exciting. Okay. And by the way, for our purposes during this class, a is always equal to 1. We never explicitly define it. So just assume it's 1 and just run with it. Fair enough? D, of course, it says where the data will end up. Does it end up in the F register, or does it end up in 0 register? And its value can be 0 and 1. And then F is the register. It can be from 0 to 255. We know for us, for this part, it's going to be from 0, hex 80 to hex FF. That's the only value we can put in there. Okay. Now, if it's not that, then and if you're dealing with the SFR register, it's kind of an interesting thing. We'll cover that later. And then also it tells you, for example, which status flags are set. Because this is an arithmetic operation, the result could be 0, could be negative, could have a carry, overflow, or digital carry. These are just basic flags that we would set. And you say, okay, who cares? We care because we can make a decision to jump someplace else based on the results of this. There's a whole set of instructions called branch instructions that you can use based on the result. And so you want to kind of know. And for us, what we focus is on 0 and carry. Those are the two we spend most of our time. Carry basically tells us the number was bigger than we could put it in our register. That's what carry means. 0 means we did the operation and we got a 0. Now, does every instruction affect all the flags? The answer is no. Then the question is, how do I know which is which? Then you go here and you look at this. For every instruction, it will tell you which flag it affects. Okay? And if it doesn't affect the flag remains the value it had before your instruction got executed. So unless your instruction is changing a flag, the flag value doesn't change. Any questions?
How do we look at the flag value? Where are those?
There's a special function register called status.
Okay.
And in the status, they put it all in there. So let's go see if we can find it. So status, can never find these things, but it's in here somewhere.
And quick question from the homework too, when
Sure.
you're done, about status.
That's what I would like to have a search button that finds it. What the heck? Let's go find it here first. Where is status? It's hiding.
Oh, it looks like FD8H says status. That's what you're looking for.
FE8H. FE.
Second column, about 3 or 4 down. Or
There, right there.
Yeah.
FD8. Yeah, there it is. There it is. So let's see if these are organized by address. I'm hoping there should be. Anyway,
It's right Yeah.
It's in there someplace. You just gotta go find it.
Scroll down just a smidge. It is. I
Oh,
just
right
saw.
there.
Yeah. It's,
Thank you. Thank you. Thank you. Okay, yeah, it's all the height. Here it is, and these are the bets. You see that you can test these bets individually, or you can do a branch. So, for example, when you say branch Z, BZ, branch on 0, it checks to see if the flag is set to Z, its Z flag is set to 1. If it is, it branches. If it's not, it doesn't. Then there's a negative side, is that a branch not 0, which does the opposite. Then you have branch carry, branch not carry, and things like that, okay?
So you can watch that in the variables in MPLAB, right?
Yeah,
Is that
absolutely.
okay? So you know what the status is. All right.
Yeah, so you can go here, you can go to your variable, and you can add another one, and you say, I want, this is an SFR register, and my SFR register, oops. So now I'm looking at the status, and if you look at the status, it's got bed 0, bed 1, bed 2. So bed 2 is set. Let's go find out what bed 2 is all about. Bed 2, 0, 1 to 0. So the result was a 0. You see that? Because this bed is set. Okay. So let's see, where were we here? Quick reference. Okay, so now we kind of talked about that. Let's go back to this, and then it tells you what it does, what the default values are, and then also gives you the machine code. So how does the computer know you're trying to add? And the reason the computer knows you're trying to add is because 001, 001, there's no other instruction that its opcode is 001, 001. There's no other one. Now, so that's how the computer knows you're trying to do add. And then it knows that next bit tells you where the destination is. The next bit tells you whether you're bank switching, and the last 8-bit tells you that which register you're messing with. Now, remember, we are computer people, and the computer people start counting at from 0. And that, if you haven't spent a lot of time in this world, sometimes we always start counting from 1. Just be careful. So when it says, I noticed somebody had a comment for me, like when you say you got 8-bit, that means you go from 0 to 7. If you got 16-bit, you're going 0 to 15, and that's a bit confusing sometimes, because in human world we always deal with. So that's and most of you, based on my past experience, you can very easily take an instruction and convert it to a machine code. Now, where things get a bit weird is when we start talking about branches. Okay, branches are a bit weird in that they don't, you got to do some arithmetics before you can figure out what the machine code is, and that is what causes a bit of trouble. So let me get to the branches real quick. Okay, so here's an example of a branch, and the equation you have to keep in mind is this equation, and that's probably by far the hardest type of instruction to go from machine code to assembly code. And what it is this is the equations you want to use, which basically says, what does that equation says? It says basically I have rewritten this just a little bit in the text and the way I talk about it. I talk about new PC is equal to the existing PC program counter plus 2 plus 2n. Okay,
So can I
n
ask you a
can be a
quick question
positive
about
number,
that?
and I'm sorry, go ahead.
As far as getting the PC, so like on the homework we had, that's just coming from the quiz. So we had like 2 pieces of the machine code, the first word and the second word.
Yeah.
And that's obviously in K, not the PC. So do you add a 0 to the 0 bit, the least significant bit, right? Not the most for the PC.
So be careful. That is GOTO. GOTO is treated completely different. Branches are different from GOTO. So hang on to GOTO. We'll get there in a minute.
Okay.
This one basically says, okay, so you've got an instruction. Let's say you've got an instruction as 0x120. This is, I don't know, something exciting. No, does nothing. I'm just making things up. So 122, you got an add WF, and then a loop is here. There's a label called loop up there, and then we have that 0x124. We have a branch to loop. Okay, this is an infinite loop, basically the way it's set up, because the branch is unconditional branch. And it says, okay, and then you say, okay, how do I find out what's this? So you say, okay, it's a branch, which means these 5 bits have to be 1101. You have no choice. Those are the values you have to put in there, so it knows it's a branch. Where do I get the n? So the way you get the n, you say, okay, the branch of the PC where it's sitting is hex. Remember, this is the other trick. These are hex numbers, so be careful with hex numbers. Hex number go from 0 to 15. When you borrow, you don't borrow 10, you borrow 16, right? That's the big difference between hexadecimal. The borrows and the carries are 16, not 10. And then you add a 2 to it, and you add a 2n, 2 times n. And remember, n is a 2's complement and can be plus and minus. And then the new PC is where I want to go, and where I want to go is 120. So this has to be equal to 0x120. Okay, so be very careful. This is going to give you, this is a real equation that you have to solve, right? It's not a complicated equation, a simple algebraic equation, except it's in the hexadecimal. So when I have a 124 plus 2, that becomes 126. I take it to the other side. So my 2n now is equal to -6. Are you with me so far? Question? All right, which means n is equal to -3. N is 10 bits, so I got to make my number to be 11 bits. Sorry, it's 11 bits. Sometimes it's 11 bits, sometimes it's 8. It just depends. You have to look at the instruction individually. So n is -3, which means I have to find 3, 10-bit 3. 10-bit 3 is going to be 0, 0, 0, 0, 0, 0, 0. I ran out of room, sorry. So that's a 3. To get a -3, what do I have to do? I have to do a 2's complement, right? 2's complement. And remember what it is. You come from the right-hand side, leave the first bit alone, first one alone, whatever it is, and then complement everything else. So the number will be 0, 1, 1, 1, 1, 1, 1, 1, 1, 1. Are we good so far? So what that means is now you've got 1, 1, 0, 1, 0 for the opcode, and for the n you've got 0, 0, 0, 0. Oh, sorry, the complemented one. 1, 1, 1, 1, 1, 1, 1, 1101. So that means this, the machine code for this instruction is actually E. No, not E. E, E, F, that's a D. D 7, right? I'm going hex. 7, F, D. So by far, this is the trickiest conversion between machine code and assembly and back and forth. So we'll get some more practice on this one, but pretty much spend a little bit of time thinking about this. This takes a little getting used to.
So you're not exactly giving it an exact address. You're just giving it the difference basically to jump back to the new address. So you're not saying go to 120, you're saying go back four bytes.
Exactly. These are relative. They're called branches are called relative addressing. So you are telling them go -3 steps or go +6 steps or whatever. And n is, that's why n is plus and minus, because you can jump back or jump forward.
Okay. So if you were at 220 or 222 and going to 226, it'd be the same code. It's just saying go back 4 steps. Okay.
So,
That makes sense.
so if somebody gives you this question, they have to tell you where the branch instruction is currently and where it needs to go. Now, you had a question about go. Any question on this one before I go off?
Actually, what's the H right there?
Oh, that's so you can say this or you can say this. Both indicate.
Oh, hex. Oh, okay, gotcha. Okay.
Any other question? Anyone else? Now, the other kind of jumping we have, branch is relative, is shorter, is only two bytes, it takes less time and all that. But there is another one. What if I just don't want to do a relative one? I want to jump anywhere in the code, and that's when we use GOTO. GOTO basically doesn't care, you don't need to know where the GOTO instruction is sitting itself, because all you say is go to this location and it goes to that particular location. So let's go ahead and take a look at the GOTO. I thought I had a GOTO in here. Oh, what? Oh, that's okay. We'll go do our own GOTO. Let's see, where can I find it? Here it is. Okay. So the other instruction we want to spend some time with is GOTO. It should be in here somewhere. GOTO right there. So GOTO instructions are kind of like this. So I want a little more space to do GOTO, because GOTO is different in that GOTO it jumps to an absolute location. So if you look at the GOTO and you look at the instruction for GOTO, no, I don't want to put it here. I can't. So let's put it here. Where is GOTO? Let me find. Oh, GOTO is here. And if you look at it, GOTO is not just 2 bytes, it's 4 bytes. It's 2 words, a much bigger instruction. Why? Because you need enough room to put enough address in there. And if you remember, memory in this chip can go from 0 to 1, F, 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 F. So you can have 21 bits. Okay, so it can address 2 megabytes. Okay, so since it does that, that's why your PC is 21 byte. That's why the memory is that big. So you got to be able to remember. You got to have room for 21 bits. If you only got 16 bits for your instruction, you don't have room for it, especially since I have to use 1, 1, 1, 0, 1, 1, 0, 0, just to say this is the opcode. Okay. By the way, the S is called S. We always put a 0 in. This is a shadow register. We make some copies of things, and we don't need to worry about it for now. Let's assume it's 0. So this says, and then for the first byte and for the second byte is 1, 1, 1. Okay, and so that you don't have any control over. But then you have other bits that tells you the address, and the way that organizes it is just a necessity. It's not really the best way to organize it. They've got K0 through K7 in the first word, and then they've got K8 to K19 on the second. Okay. Now, if you now if you look at this, you say, wait a minute, this is kind of weird. So how does this work? So I've got K0 and I've got K19. When I put these together, K0 through K7, K8, K19, I put them together. I've only got 20 bits. Where is the 21st bit? And their answer is that, remember, we always start executing code at location 0, right? All of our instructions are either 2 bytes or 4 bytes, so we never end up on an odd address. Our address is always even, which means what? Which means that the least significant bit of the address is always 0. So you use this to figure out what the next PC is. So the PC looks like here. Are you with me? Does that make sense at all?
Yeah, so in the homework, and we don't have to go through the exact answers, but in the homework, you're asking for the machine code for the function, or basically in hex, what is the machine code for the next address that it's asking for, which ends up being.
So let's do it.
3960.
Let's do it. Let's do it. See if we can make it happen. So hang on here. So we understand this. Anybody has question on the kind of the basic concept? If you don't have, so let's do an example. We'll do a different example than them. So let's say somebody gives you an instruction at location 0x90. You've got a go to instruction. Go to next. And somewhere down below here at location 0x1293, that can't be, has to be even, right? So make it 6. You can never have an instruction starts on a non, just the no. Yeah, there was a question about BSR. I'll get to that in a minute. And let's say this is location next. So the go to basically says, go ahead and jump there. So what we're going to do is we say, okay, next is right here, which means my case, if you break this up, right, your K0 through K19, right, it's going to be 6. These are hex values. So 6 is going to be 0, 1, 1, 0. 9 is going to be 1, 0, 1. And then 2 is going to be 0, 1, 0, 0, 0, and 1 is going to be 1, 0, 0, 0, and the rest are 0. Okay, so K19 is back here somewhere. K0 is here. So this is going to be K0, K1, K2, K3, K4, K5, K6. This is K7, right? 8 bits. And this is K8. So if I go back up here, what I'm going to do, so my K, let me see if there's another nice color I can use, maybe a blue. So that means from here, I just copy my K0 here. So it's got a 0, 1, 1, 0. And then I've got 1, 0, 0, 1. And then from K8 to K19, I've got 0, 1, 0, 0. There's too many zeros here. That's just. And then 1, the rest of these are 0 for K19, okay? So if they want the machine code for this one, the first one is going to be EC9 96. So the first byte is going to be 0x E696. Oh,
So
no.
isn't the go-to function should be EF? Isn't that 1111?
Is it? Let me double check.
So
I may have copied the opcode incorrectly, so let's go back and check. Go to, yep, you're right. Oh, what I was looking at. Anyway, yeah, you're right. Should be 111. So let me go back and fix that. Yep, so this is one for the output side. I was looking at something else mostly. So it would be EF96, okay? And then the next instruction is going to be basically, first it's going to be 2, right? Oh, I messed up. What did I mess up? No, that's right. That's right. No, I messed up. What did I mess up? Anybody?
I don't know, but I might have made the same mistake because I'm getting this answer on the homework, and it says I was wrong.
Remember in the PC, if you've got the this is the PC, right?
Well, that's the K and then a 0 at the end.
No.
would be
This is the
right?
PC because remember, this is the PC. This is where you want to jump, right? Oops. This is where you want to jump. That's the value of the PC I wrote here. Are you with me? Anybody? Or does anybody ask questions?
Yes,
This is the PC.
So the K value, that is the PC minus the 0 at the least
Yeah,
significant bit, right?
Yeah, that's what I messed up.
So do you add that 0 and then you go
I have
from
to
there?
kill the 0. I have to throw that 0 away, and then this becomes K0. This becomes K7. This becomes K8, and then on and on. That was the error. You see that?
I'm confused how that works because the opcode is showing all Ks, right?
Right. So now so you see where K0 through K7 is?
Mm-hmm.
I'm going to take these guys and put it up here. So this is going to be 1, 1, 0, 1, and this is going to be 0, 0, 1, 0. It's basically this piece.
So the 3960 is going to be 21 bits starting with 0, 6, and then you just cut off the 0.
To make it 20 bits to
0.
fit into K0 through K19. You see that?
Okay. Yep, that makes sense. Okay.
So that means,
I think I added a 0.
So that means this is incorrect, and the code really is 0xEF4. I'm basically taking each one of these and translating them. 4, and that is a B, I think. And then down here, you basically have K8 is 1, 0, 0, 1, and the rest are zeros. You see that? Which means the second byte is going to be 0xF 0, 0, 9. So this would be the machine code for our example. And once again, it is okay for you to listen to me doing it, but the real value comes in if you were able to do it yourself and see where you run into problem, if you get a different answer, and then having a conversation maybe next time we get together, okay? So let me do one more thing, and before you guys take off, there was a question from Daniel regarding BSR, and I wanted to just cover that real quick before you guys take off today. And actually, if folks who can hang around, maybe we can kind of get you guys, and you want to start the lab before Thursday, we can kind of talk about LAB3 as well. So, so the question that Daniel had to do with the BSR and what a BSR is. We're not going to use it here. It's a very, very specific thing to this processor. It's not very common outside, so I don't want to drag you through it, but it's good for you to have heard it. Now, if you are as old as I am and worked with 8086 when it first came out, the very first Windows processor that came out, you would be very interested in this because they had everything was Windows, because the processor only had 64K of memory. And if you wanted to have more, what you had to do is have many, many 64Ks and have a register that flips which 64K you're looking for. It's called, used to be called segment. These guys call it bank. So in reality, what a BSR does it basically moves. You only have your memory for SFR and GPR, the special function register and the graph and the general purpose register, all fit only between basically location 0, 0 to location 0, I'm sorry, 0, 0, just 2 and 0 F. So all the memory, data memory, these are data memory, it fits in here. So you have to fit it in here. So the way they do it, they have this other register called BSR that can go from 0 to 15. And based on what you put in the SFR, the values, what you put into the BSR, the bank register, you have your location move around. So what we are doing, we are assuming A is equal to 1, which means we are using BFR, because if you set the A to 0, you are not using BSR. We have the A equal to, we are using BSR, and BSR is always set to 0. So for us, the GPRs appear here and the SFRs appear here, okay? But they're all mapped perfectly well. The computer knows how to deal with it. You don't have to worry about them. So all you have to worry about is that if you want to allocate memory, your memories have to go from 0 to 0xFF. Now, if you had additional memory, you had added your own memory to your register and you want to go someplace else, then you can use this bank register and say it's 1, then it looks for the memory locations that are here. And then if you set it to 2, so if you set it to 1, it would look at 100 to 1FF. If you set it to 2, it would look at 200 to 2FF, and on and on. In our case, those places are empty.